rather different from what you have done in the past. And then we also need to introduce quantum theory today. So this will be in, not instead of the intro to quantum theory that I'll give you after relativity, but a supplement to it, and oftentimes what I'll be doing is referring back to things that I've talked about here, rather than going through everything again. And so you can think of this first little part as being kind of like lecture material, but lecture material that you don't need to be totally proficient in at an exam level until we're done with relativity. So this lab is a relatively straightforward lab. It's I think the easiest lab to take data on. So what I think I'm probably going to do with this first lab is make it work a little less, just because I'm going to be kind of critical on how you write up the labs, and I don't want it to count too much against you, until you see what it is that I'm really looking for. But you can ask me anytime, and I can say, well, yeah, that's looking pretty good. Or maybe you should work a little more on this aspect of it. Also, before I forget, next week I have a training thing they make me do this every year for hiring new instructors. And so that goes from 9 to 10:30. So next Friday, what I want to do, instead of having our regular lab, is I want to give you the quiz on Friday. And so instead of giving you the quiz on Thursday, I'll have one more day to introduce and talk about stuff from the quiz. We'll also have that time for maybe a little bit of an in-class activity at the end of class where I can ask you some quiz-like questions on it. We can work on that together, and so that'll give you a little more time to get ready for the quiz. So next Friday, then, we'll have a quiz in here at 10:30, which is when my training thing ends. But I'm not expecting that that's going to take 2 hours, right? And so what I'd like you to do is look over your data this week, and if it looks like you need more data, you can take more data. Now, some people last semester, or last year when I taught this lab, didn't realize everything that was expecting to be analyzed in the lab, and they had to come back and take a whole bunch more data. So be sure to pay attention as I go through this, and Mark is recording it, so I'll post this so that you can refer to it. This lab will be due, first lab will be due 2 weeks from today. And this will be worth maybe, I'm thinking, 65% or 70% of a regular lab, just because it's a little bit shorter, not quite as many things to analyze, data gathering is easier, and I think the write-up will probably be a little easier too. And then that'll also give you a chance to see, oh heck, I should have done this and that and not have it count as many points against you. Okay, so the first thing I want to do then, before we get into the actual process of the lab and how to write it, is to do the lecture material on the intro to quantum physics. And so I'm going to be spending a little bit of time on that now, and this we can consider to be lecture type material. Are there any questions about anything before I get started? Yeah.
Are we we turn in our in-class problems from yesterday?
Yeah, you can turn those in today. If you had any problems with any of them, I could take a look at it with you too. That'd be great if you could turn those in today. Here is the problem that we have back in 1900. We have, for black body radiation, we define black body radiation and by the way, we'll have a whole lab on black body radiation later. But black body radiation basically is a spectrum of frequencies of electromagnetic radiation that is given off by an object at a certain temperature. Okay, and so in the black there, or in the, the red, we have, this is our observed black body radiation curve for an object at a particular temperature. So in the vertical axis here we have intensity, and intensity has units of power per unit area. And on the bottom axis we have wavelength. And so this would be the intensity of different forms of electromagnetic radiation given by an object at a particular temperature. So this was a subject from Physics 208A that you may not remember all of the details of it, but this curve is for a certain temperature. So each temperature has a different curve. So this might be, say, the black body radiation for the sun. This temperature, I'm just making this up, but maybe this is 5,000 Kelvin. And then this is going to have the same shape, but this might be the black body radiation curve for a red hot fire. Okay, and so that might glow kind of orangish red. And so that would be with a peak frequency here that is lower. Okay, so that would be the, that actually, I should say here, that isn't really where it's peaking out. It's peaking out in the infrared. And so the red would be here. And so with a red hot fire, at maybe, say, 300 degrees centigrade, what you'd see is the red, and then this would be the orange and the yellow, because that's smaller wavelength, green, blue, violet. But the red part would give off more visible radiation than the orange would, and that would be a lot more than the blue would. And so when you mix that all together, it's kind of an orangish glow to the fire. But you put your hands there, and it warms you up, because the peak intensity is in the infrared. But it's also giving off some X-rays, which would be really low wavelengths here, and it's also giving off some radio waves right there. So it's a whole spectrum of electromagnetic waves that's given off by a black body. So we define a black body, it doesn't have to be black. It's just an object with atoms that are fairly close together that's in thermal equilibrium. So in other words, it's not a gas. It's It's usually some kind of a substance where the atoms are fairly close together, it's in thermal equilibrium. So all the little electrons then that are moving around at a certain temperature have a distribution of different velocities. So there's like what we call a Maxwell-Boltzmann distribution of velocities for these molecules. And so some of the molecules are going to be moving faster and create higher frequency electromagnetic waves when the electrons jiggle more, and some will be moving slower and will give off lower frequencies. So basically you get a whole power spectrum of the entire electromagnetic spectrum here in a single object. And it turns out that our bodies, if we're sedentary, the amount of energy that we lose from black body radiation is about half of our total energy loss. Now, if we're running or something, then we might have conduction or convection. But radiation is about half of the energy loss of our bodies if we're not moving too fast. And so this is kind of a big deal. And so when we plot one of these curves, the peak temperature here, or the peak intensity of radiation corresponds oftentimes to the color that we see for the object. And so in this case then for the sun, this would be kind of yellow or green. There, and that would be the peak. But the sun would also give off, if this were, say, the surface temperature of the sun that we're talking about. So that's clearly not a black body. The sun is anything but black. But it still is radiating like a black body because it's in thermal equilibrium with itself and the atoms are squeezed by gravity forces. You know, it's in a plasma state so that they're relatively close together. Okay, and so this was all known, this was all measured, but they were trying to, back in 1900, they were trying to explain this curve. Why does it look this way? And so at the time, they believed that energy is continuous. So what do I mean by continuous here? Well, I mean that you should be able to produce any energy you want on the number line, any value for the energy, by just changing the frequency of the source and the intensity of the source. You should be able to get any energy you want. But with matter, it had already been determined that if you cut something in half, and then you cut that half in half again, then you cut that half in half again, the Greeks wondered, is there a point where if you took a substance and you cut the half in half and the half in half and the half in half, do you ever get down to an individual unit of this substance? And the Greeks somehow deduced that if you do this with matter, you eventually get to a basic unit called the atom. And so some people started wondering, well, is energy like that too? If you took an electromagnetic wave and cut that in half, and then cut that half in half again, and cut that half in half again, could you continue the process of subdivision infinitely? Or would you eventually get down to a basic unit of electromagnetic radiation? And so if it's continuous, then you could continue this process of subdivision forever. But matter is not continuous. So we say then that matter is quantized. But it's like, how can energy be that way? Energy just seems like it's smooth and continuous. Was there a question? That is my hand back there. Go ahead. Yeah.
Can I go back to the curve really quick?
Yeah,
With the
sure.
colors? Did you say, like, when you're labeling it, the x-axis, those little letters I can't really see, is that G slash Y for green slash yellow on that middle,
Right, yeah, so this would be, if you look at the sun, say from space, it has kind of a greenish tint to it, but
oh,
after the light goes through the atmosphere, some of the higher frequency, because the scattering is taken out, and looks more yellow.
okay, so that is what we would technically see.
Yeah, so that's kind of our color perception, which is a weighted mix of all of the different colors, but the sun's peak intensity is in the visible range. And so that's the reason why we see visible light, is that that's the kind of light that the sun puts out the most of. If we saw an X-ray or in radio waves, we'd need eyes the size of trash can lids to pull in enough light to form an image. And so it's just natural then that we would sense the kind of light that the sun puts out the most of. And there's also a second reason why we see invisible, and that is that visible light travels through water, and most of the theories of evolution indicate that we started in the water. And so we'd be blind, we wouldn't have a sense of vision if we didn't see in the visible range. Any other questions? Okay, so the problem though, if energy is continuous, is that you get this curve that is labeled by classical theory for the black body radiation for the sun. And I, by the way, have all of these calculations. If anybody wants to go through them with me, and you want to get into it deeper, I can go over all the math of this with you. But this is the prediction of classical physics for a black body radiation curve. And so what this tells us then is that as the wavelength gets smaller, for objects like the sun, we should have what's called the ultraviolet catastrophe. And if it's the ultraviolet catastrophe, it would be the X-ray nightmare, because it just keeps going up. It approaches infinity as the wavelength goes to zero. So this gave rise to the wrong answer. It predicted, with continuous spread of electromagnetic waves that could take on any value, which means you could keep this process of subdivision going on forever and you'd still have a little bit of energy. That gave the wrong answer. It gave the ultraviolet catastrophe. So here, as wavelength gets smaller, eventually this is going to be UV. And so we see that that would be the value for the ultraviolet, but it seemed to be this value. And ultraviolet is ionizing radiation, which means that it would destroy all life. And so we wouldn't even be here if energy is continuous. So this guy named Planck comes along, and he goes, well, I'd like to try to fit this curve. And so I'm going to make an assumption. And that assumption, and he actually didn't even believe his assumption. Einstein had to convince him that he was right. He didn't believe that this was true. But Planck assumed that there is an elementary unit of electromagnetic radiation. Which we now call the photon. And so we can then think of this electromagnetic wave as being made up of a whole bunch of photons, in just the same way as we can think of this piece of matter here as being made up of a whole bunch of atoms. And so this is our elementary building block then. And so he assumed then that the energy of the electromagnetic wave is equal to some integer times Planck's constant times the frequency. So this is some whole number, 1, 2, 3, da, da, da. H, appropriately, is called Planck's constant. And F is called the frequency. And so that means then that a single photon has the smallest amount of energy that you can have in an electromagnetic wave. But usually we don't write it in terms of frequency, we write it in terms of wavelength. And so if we say speed of light is frequency times wavelength, then we can rewrite the frequency as the speed of light divided by the wavelength. So we write it like this. E is equal to hc over lambda. And so that's the energy of a single photon. This, of course, created a lot of controversy in the scientific community. And this is before matter was found to have wave-like properties as well. And so people are arguing, this just doesn't make any sense because how could you possibly have a wave that is made out of particles? It doesn't seem like those two formulations are compatible with each other. And yet, when Planck assumed this, and he worked the math through, he gets the right answer. As I mentioned, Planck didn't believe it either. He was just kind of desperate and looking for some kind of a mathematical tool, like the square root of -1 helps you solve different kinds of equations, say roots of equations like we were talking about last time. But the square root of -1 goes away in the end. And so that's what Planck was thinking would happen, is that this assumption would disappear in the end and it would just be an operator that would help me get the right answer. But eventually Einstein comes along and he explains what's called the photoelectric effect by using the principle of these photons. In the photoelectric effect, and this, by the way, is how you get those clumps of electrons to pop up so they can be accelerated in the pulse laser at the Stanford Linear Accelerator, is you take a certain frequency of light and shine it down onto the metal. And what we find is that as you increase the frequency, eventually electrons are ejected, but always with the same velocity. And so I'm going to talk much more about this later, but the fact that they always have the same velocity means that they're just gulping down one photon at a time. They can't take two at once. And that's why every electron that comes off of here has the same energy, even if you have a stronger beam. This beam could be 10 times stronger, but still every electron comes off with the same energy. And what that tells us is that the electrons are only taking a certain amount of that energy. And that's what verified, and Einstein didn't get the Nobel Prize for relativity, he got it for the photoelectric effect in 1921 because of this discovery. And even though Einstein, as we'll see, had a very strong dislike for quantum mechanics later on, he is actually one of the founding fathers of quantum mechanics as well. Okay, so we can explain a lot of things then with this photon nature of light. One thing that we can explain is the spectrum of light that's given off by atoms. For example, if we look at hydrogen, which is the top one there, we see that there's only a few frequencies that are given off by hydrogen. So how do we explain that? Well, if we think of the proton as being the nucleus and the electron is orbiting around, the electron, as it turns out, ends up only in specific shells that surround the nucleus. And if the electron can be excited up to a higher energy state, that electron can drop back down, then it always releases the same amount of energy. And that energy is in the form of a visible or an infrared or an ultraviolet photon. Okay? And so as electrons change their energy, the electrons can produce photons if they're accelerated. So the electrons can change their energy either by absorbing or radiating photons. And so when you give electrons a certain amount of energy, you could think of that either as being due to a collision with other electrons, or you could have a photon come in and do it, just the way that I described last time. Remember with momentum times speed of light equals e? So we saw then that a photon has momentum. Now momentum can be imparted to an electron, but only in specific amounts. Okay, so it can only gobble down a little bit at a time. So it can't just take a continuous amount of energy that's coming. It has to take it in these discrete bundles called photons. Just like a chunk of matter, you can increase its mass, but not through any variation. It has to be integer multiples of an atom. That gives you a bigger mass. Similarly here, an object having more energy means that it would have to absorb individual photons one after another in order to produce the effect that is observed. Now, why don't we see this all the time? Well, because Planck's constant is very small. So this is what we call a quantum effect. H is equal to 6.63 times 10 to the minus 34, and that has units of joules seconds. So it's very small, and because it's so small, it tends to have more of an effect in subatomic physics than it does in our macroscopic world. Okay, so that's the introduction to photons and how that relates to Planck's constant. Are there any questions about that introduction? Okay, next, what I want to do is take a look at how that relates to this lab. In doing this, I'm also going to need to discuss semiconductors. So what is a semiconductor? Well, I've downloaded a couple of short videos here onto the home page. Right below important dates, there are the videos I had on the electromagnetic radiation, and then I've also put two more down here now. One of them's on LED, and the other one is on diode operation. So let me just talk a little bit about how semiconductors work and how a diode works. If we take a chunk of silicon and we try to send a current through it, nothing's going to happen. It's an insulator. But silicon has some interesting properties. because of the fact that it is in the same column on the periodic table as carbon, it has 4 electrons in its outermost valence shell, and this gives it an opportunity to connect in with other silicon atoms in a way that allows for a lot of different kinds of chemistry to take place. And this is, by the way, the reason why carbon is so good for life, is that it has a lot of combining power. But because it's a smaller atom than silicon, some of the electron shells can overlap with each other and create better bonds, so you can get more complex molecules. So it's perhaps less likely that you could have silicon-based life, but it doesn't mean that it doesn't exist out there. It's just there are more barriers to it. But the silicon crystal, it's an insulator, but if you add a little bit of impurity, you can make it into what we call a semiconductor. Okay, and the kind of impurities that usually work are ones that have one less or one more electron in the valence shell. So an example then would be germanium. See, germanium is in the column to the left, and so that has one less electron than silicon does. In the outermost shell in silicon. And so let's just put some germanium into here, and that's called doping it. Okay, so if we dope the silicon crystal with germanium, we can get basically a bunch of little vacancies here where electrons should fit in. But there's no electron because there's one less electron than silicon in the outermost shell. And so this creates holes. So they're not really positive charged, they're just less negative. So the rest of the silicon crystals have the electrons all in these perfect positions at tetrahedral angles or whatever. But then with germanium, there's like a vacancy there where there's less electrons. And so that's the same, less negative is like more positive. So we can say then that these holes are produced. Now how much germanium do we need to make this into a semiconductor? The answer is just a few parts in a billion is all we need. And so this is also one of the reasons why there could be differences in the production of the semiconductor that can give rise to a little bit different results for us in lab. Questions?
Isn't germanium in the same column as silicon?
Oh, gallium, I didn't. Sorry. Yeah, that fixes it. A. Turn the E into an A. Okay, and so if we hook this up, we'll call this a P-type conductor because it's got these little positive holes in there. And then we apply a voltage to it, and now the electrons, remember, go from negative to positive, the electrons can leapfrog across these holes. Okay? And so the electrons then can bridge this insulating gap, and so as the electrons go this way, the holes go this way. So the direction of hole motion is actually in the same direction as positive conventional current. So this is the only time that I am aware of where positive conventional current is actually caused by something that's equivalent to positive charge carriers, even though it's the negative electrons moving in the other direction. So if that doesn't make sense to you, let's just say that you're in traffic like this. and somebody pulls out, so there's a gap in the traffic, okay? And so then what do? You pull up this way to this point. So this is the car direction. Let the hole move this way. And so that's what's happening here. So the electrons move this way, that causes the holes to move the other way. And so we get this kind of a conduction happen. You could also, another possibility is to put in a dopant that has one extra electron. And so there are different substances that can do this, but typically we're looking one over from carbon to the right, and so that would be like arsenic. By the way, arsenic acts a lot like phosphorus because of its similar chemical structure. And so it can get into your, if it gets into your system, it takes the place of the phosphorus molecules. But it doesn't have the right chemistry, and so that's why arsenic is a poison. So here arsenic has one extra electron. So an N-type material has extra electrons that are just kind of jammed in there. And so what this does is this makes the system more conductive for the opposite reason, is there are extra electrons already in there. And so if we were really going to look at this thing rigorously, we would use solid state physics. We'd get into all this stuff with the conduction band, the valence band, and all of that stuff. But it affects what we call the conduction band in a favorable way to allow for electrons to flow. And so the electron can push on this side, that'll push this one out, and this one will come in, and so the electrons can flow just fine in an N-type material. But what a diode essentially is two of these put together, back to back. Let's say here we've got the P, and here we've got the N. And so then this is the transition region between the P and the N. And so let's see what happens then if we hook up the battery like this. Well, then that's going to try to generate a current this way, which means that electrons will tend to go this way. Okay, and so that means that electrons will move this way, because this is the more negative side of the battery, and so they're actually pushed up against this transition junction. But the electrons are going to tend to be sucked out this way. So the electrons go out this way, and that moves the holes in the opposite direction toward the center. Okay, so the electrons move this way, the holes move that way for what we call a forward bias voltage. And so this is called forward bias because the current can flow. But the trick here is that there's a little bit of a barrier between the P and the N. Okay, and so this is what we sometimes call a depletion region, but the depletion region is thin. So this creates an energy barrier. So if we plot the potential energy, V On the left-hand side, this is the depletion region. Then there's gonna be a little jump here, and then it's gonna jump down to a lower value here. So this is the barrier that's associated with the depletion region. This is the voltage above. So this is a higher state of voltage. And this is the voltage below. Like that. And by the way, in some of the things you've seen, it talks about stopping voltage. This lab has nothing to do with stopping voltage. The previous instructor, bless his heart, has done so much to help this lab, but he had the physics wrong on this. This is a forward bias voltage that drives electrons over this peak. Okay, and so what happens then is, as the electrons are moving, and actually, because the electrons are going this way, I should probably figure out the other way. Come in like this, bump up like that, and then down. So here are the electrons coming in this way. And then they're going to experience this energy gap, and they're going to drop down to that lower state. But you have to push the voltage to this point to get them over the hill. Okay, so it's like if you're pushing a car. And you only push it this far, then it's just going to come back down again. You've got to give it enough energy to push it up over the hill. So it has to have enough kinetic energy here so it'll go over, and then kinetic energy will turn into potential energy, and then it can go off on the other side. And so this forward bias then means that we need a certain critical voltage to start the electrons moving. So then they jump over this, and in an LED, this is still a PN junction, that the properties of this are set up so that it takes just the amount of voltage that's required so that the difference in voltage is released as a photon. So our photon then comes off like that. The electron goes over, it's pushed over by this critical voltage, and then it drops down to that lower voltage. And as the electron drops to this lower voltage, just like the electron in the atom drops down to a lower energy state and gives off a photon of light that you saw in that hydrogen spectrum, these things are designed so that that difference in energy is just enough under the conditions that are set up within the crystal so that that energy is turned into light. And so then this photon is released. Okay, and so if you add more and more voltage, then you get more electrons going over, but all with the same frequency. Okay, so if you add more voltage, it just means that the electrons then can go over, and but more of them can do it. Okay, the more energy we have, the more. And so the equation for this is the energy gain the energy lost, because it already has that energy. It gained it, but now it's losing it. Energy lost. Equals the energy of a photon, hc over lambda, times n, plus phi, where phi here is equal to the energy dissipated in the semiconductor. So this is kind of a funny term. When you produce light in a regular filament, what happens is you heat the filament up with a big voltage here. You heat it up, then it has a black body radiation curve, and it produces light at a certain frequency. Okay, and so you've got to heat this thing up to a really high, super high temperature. So you're losing a ton of energy here. A whole ton, and that's why light-emitting diodes are so much more energy efficient than regular light bulbs. Is that a regular light bulb requires black body radiation to produce it, but in order to do that, you've got to get the temperature way up. So that means that a good portion of your energy is lost in heat. Here, phi is relatively small, but this is the energy lost while making the transition. Now, in general, this energy lost is going to be different for different types of semiconductors. But for the ones that we're dealing with in lab today, we're going to make the crude assumption that the energy losses are all the same for every semiconductor. And so that's going to create a little bit of error here. Well, I should say for all the diodes. LEDs. It's not going to be, because each LED has a different value for that voltage, because you're going to have some LEDs that produce blue light, some that produce red light, and so that forward bias voltage is going to be different. If that forward bias voltage is going to be different, that means the property of the material is going to be different, and this energy term could not be always considered to be the same. But for simplicity, we're going to assume that that's the case in this lab. So what we can do then is, because it takes different amounts of energy, and so here's our setup. We've got a bunch of LEDs here. 1, 2, 3, 4, 5, 6, 7. Each one of them has a different forward bias potential to get electrons started. And so here on the left-hand side, this is very easy to set up. You don't have to do a lot of circuit things. You just hook up the voltage. We want to measure the voltage across here. We want to measure the current across here. And then this is going to be a constant source of input voltage here. That's going to come in on the left-hand side. And then we can adjust the amount of voltage that's actually flowing through the circuit by turning this amplitude knob. Okay, so this amplitude knob here will adjust that. So notice I've got this thing set to the green LED. And so there's a certain point where it just comes on. And before that point, it's not coming on. That's because we're below the energy threshold that'll push that electron up over the top of the hill. Okay, but once we get to that point, then photons start to flow. So we get more and more and more photons flowing until we get the light as bright as we want. Then we can go to the blue one, and we've got the same kind of thing happening. Yellow one. But there's a different forward bias voltage that gets the process going with each one. But it's not a reverse bias. That was an error that was made by the previous instructor. So you'll see that in a couple of things that are printed out, but that's not correct. Okay, so in terms of the voltage then, what is the energy of the electron initially? Well, we know that energy from physics 208b is equal to Q times V, where V is the electric potential difference that the charge is accelerated through. So we can plug that in here, and we get Q electron times V. And so now let's back off on the voltage until there's only enough energy for one photon to go. Okay, because we don't know what N is. That's an unknown in that equation. And as long as we've got a ton of these photons going here, we don't know what that number is. Okay, so we back off until the current in the circuit goes to 0. So we've got the current being measured by the second meter here. And so you can use this little thing and you can look through and you can see, but you want to back off on the voltage until N equals 1 in that equation. Which means when the light first, the lowest voltage, when the light just goes off, that's what we want, and that'll be N equals 1. So the minimum voltage is when essentially you just barely stop the current. And so you may be looking with your eyes and say, well, okay, it's off now, but your cones or your rods in your retina don't have an infinite amount of light resolution sensitivity. And so when you see the thing go out, there's still a little bit of current going. And so you'll want to set this thing, but that tells you when to really pay attention here and look at the current meter. And you set this to microamps, not milliamps, because you want it to just go to 0 when it's microamps. If it's milliamps, then you might be getting N equals 20 or 30 or 40. You don't know what that number is for N. But you want it to just go to 0, which means you just barely have enough energy for one electron only. Okay, so when V equals V minimum, N equals 1, we get EV equals HC over lambda plus V. Okay, and so now we can plot the voltage versus 1 over lambda to get Planck's constant. And so that's our goal here, is to find Planck's constant. But we can't do it without knowing what phi is, right? And so if we plot this thing up, then this will actually be negative, right? Because it's energy that's lost from the system. Plus or minus this. You got this amount of energy. No, it's plus. Okay. And so we got V then equals HC over Q electron times 1 over lambda plus Q over QE. And so we can plot this up. This corresponds to a y intercept. And so we plot this versus 1 over lambda. We should end up with something that doesn't intersect at the origin. Maybe it's up here, maybe it's down there. Phi plus. So E minus phi is equal to that. And so that would shift it up this way. So this would be your voltage versus 1 over lambda. And so this intercept here would essentially be something like phi average over QE. And then each one of these is going to plot at a larger and larger value for 1 over lambda. Because we need more voltage to get a bigger value for 1 over lambda. That means lambda is smaller, so 1 over lambda is bigger. Okay, and so you should be able to plot these up, but these points, and this is the V minimum for diode 1, 2, 3, 4. So that would be this value for V minimum. This would be V minimum for diode 3. This would be V minimum for diode 2. And this would be the associated wavelengths that are associated with each diode. And so the slope of that curve then, even though we don't know what this intercept value is going to look like, should be equal to HC over QE. Which means then that you can solve for Planck's constant. Because the charge on an electron and the speed of light, we'll assume, are known. Okay, and so we're going to want to do it each step then, and let's just go to a couple of these things that I hope maybe you had a chance to look at them. That here, if we go to, let's see, Planck, this is the one here. It's a whole set of different little things. Here, it's a nice little introduction. Nice little introduction, classroom fundamentals. Has anyone had a chance to look at this yet? So, as we go through, it just talks a little bit about what Planck did, what these things are. But then here, this is kind of important. How we get each of these values for V is going to require a plot of its own. And so this is something, this is where a lot of people kind of failed last time and had to come back and redo this result. But